This video is about the dot product, specifically the dot product in 2 and 3 dimensions. For two vectors u and v, the dot product is the sum of the products of their respective components. The dot product will always be a number, not a vector. And if you're dealing with two-dimensional vectors, this means you have to add the products of the two respective components, and if the vectors are three-dimensional, you have to add the product of three respective components. Let's see an example. Compute the dot product u dot v of the vector u with components 2, minus 1, 5, and the vector v with components 3, 2, minus 7. U dot v is the product of the first components, namely 2 and 3, plus the product of the second components, namely minus 1 and 2, plus the product of the third components, 5 and negative 7. That's equal to 6 minus 2 minus 35. That's minus 37 plus 6, which equals minus 31. Another example, if u has components 5, negative 7, and the vector v has component 4, 1, let's compute u dot v times the vector v, the vector u dotted with the vector u plus v, and the magnitude of the vector v. Starting with example 1, u dot v times the vector v, that's equal to 5 times 4 plus minus 7 times 1 times the vector v, which has components 4, 1. Recall that the dot product is a number, so we're thinking of the vector u dot v as a scalar times the vector v. 5 times 4 is 20, minus 7 is 13, so we have 13, that's the scalar, multiplied by the vector v, which has components 4, 1. And when we multiply a scalar by a vector, we do that component-wise, so the vector u dot v times v has components 13 times 4, which is 52, and the second component is 13 times 1, which is 13. Example 2, we have the vector u dotted with the vector u plus v. So the final result will be a number in this case. That's equal to the vector u, which has components 5, negative 7, dotted with the vectors u plus v, 5, negative 7, plus 4, 1. That's equal to the vector u dotted with the sum of the vectors u and v. And we do this component-wise, so we add the vectors component-wise. 5 plus 4 is 9, and minus 7 plus 1 is negative 6. Now we dot these two vectors. We have 5 times 9 plus minus 7 times minus 6. That's 45 plus 42, which equals 87. Example 3, let's compute the magnitude of the vector v. That is the square root of 4 squared plus 1 squared. That's the square root of 16 plus 1, which equals square root of 17. Now let's talk about the angle between two vectors. The angle between two non-zero vectors u and v is defined as the angle theta, which lies in the closed interval 0 to pi between the standard position vectors of u and v. And to find theta, we use the equation cosine theta is the dot product divided by the product of the magnitudes. Of course, if we want theta, we apply cosine inverse on both sides to get theta equals cosine inverse of u dot v divided by the product of their magnitudes. Here's an example. Find the angle between vectors u with components 1 minus 6, 2 and vector v with components 3 minus 1 minus 4. To find the angle theta between vectors u and v, we're going to use the equation cosine theta equals u dot v divided by the product of the magnitude of u and the magnitude of v. Let's start out by computing u dot v, magnitude of u, and magnitude of v first. U dot v is 1 times 3 plus negative 6 times negative 1 plus 2 times negative 4. That's 3 plus 6 minus 8, which equals 1. Magnitude of u equals square root of 1 squared plus minus 6 squared plus 2 squared. That's square root 1 plus 36 plus 4, which equals square root of 41. Magnitude of v is the square root of 3 squared plus minus 1 squared plus minus 4 squared. That's equal to square root of 9 plus 1 plus 16, which is the square root of 26. Cosine theta is u dot v divided by the product of magnitude u and magnitude v, which equals 1 over square root of 41 times the square root of 26. So theta is cosine inverse 1 over square root of 41 times square root of 26. Using a calculator and making sure the calculator is set in degrees, that's roughly 88 6.24 degrees. Notice this angle falls in the allowed range for theta, which is 0 to pi radians, or 0 to 180 degrees. Now let's talk about the components of a vector u with respect to another vector v. Suppose u and v are non-zero vectors satisfying the following three conditions. Condition number 1 is u is the sum of two vectors, w1 and w2. Condition number 2, w1 and w2 are orthogonal or perpendicular to one another. And condition number 3, w1 is parallel to vector v. This means that w1 has the same or opposite direction as v. You can see these three conditions in the figure below, when theta is an acute angle and theta is an obtuse angle. When theta is acute, you can see using the parallelogram rule that the vector u is the sum of vectors w1 and w2. You can see that w1 and w2 are orthogonal. And you can see that the vector w1 has the same direction as vector v. So they're parallel in that sense. When theta is an obtuse angle, again notice using the parallelogram rule, vector u is the sum of vectors w1 and w2. w1 and w2 are orthogonal, and vector w1 has the opposite direction as vector v. We call w1 and w2 the vector components of u with respect to v. We call w1 the projection of u onto v, and we denote it by projection of u onto v, like so. And the vector w2 can be found by doing u minus w1. This follows easily from the first condition. This decomposition of a vector u into two components with respect to the vector v is useful for solving a wide range of problems. Here's an example. Find the components of the vector u, 3 minus 5, with respect to the vector v, 6, 2. Let's compute the dot product first. U dot v is equal to 3 times 6 plus minus 5 times 2. That's 18 minus 10, which is 8. We need the magnitude of v squared, that is 6 squared plus 2 squared, which is 36 plus 4, which equals 40. The vector w1, which is parallel to v, that's one of the components of u with respect to v, w1 is the projection of the vector u onto the vector v. That is given by u dot v divided by the magnitude of v squared. That's why I found those first, times the vector v. That's equal to u dot v, which we found that to be 8, divided by the magnitude of v squared, which we found out to be 40, times the vector v, which has components 6, 2. 8 over 40 simplifies to 1/5. We multiply that by 6 and 2 to get 6 over 5, 2 over 5. These are the components of the vector W1, which is parallel to the vector V. It is the projection of the vector U onto the vector V. Now, to find W2, I'm going to use W2 equals U minus W1. So, W2 equals U minus W1. That's the vector 3 minus 5 minus W1, which we found to be 6 over 5, 2 over 5. We subtract component-wise, so 3 minus 6 over 5 minus 5 minus 2 over 5. That's 15 over 5 minus 6 over 5 minus 25 over 5 minus 2 over 5. So the vector W2 has components 9 over 5 minus 27 over 5. And W1 and W2 are the components of the vector U with respect to the vector V. An application of the dot product is computing the work done by a constant force to move an object along a line of motion. More specifically, the work done by a constant force F as its point of application moves along vector PQ, illustrated in the picture, is the dot product of F and PQ. We're going to capitalize on this to solve the following problem. A man pulls a wagon by exerting a force of 20 pounds on the handle. If the handle makes 60 degrees with the horizontal, find the work done in moving the wagon 100 feet. I drew a simplified version of the figure on the right-hand side of the screen. You can see the force F in red, making 60 degrees with the x-axis, which is the horizontal. And the wagon moves along the vector PQ, which is illustrated in blue. This is also parallel to the x-axis. To compute the work done in moving the wagon 100 feet, I'm going to use the formula that the work is the dot product of the force and the vector PQ. So, W is equal to the dot product of the force F and the vector PQ. We know the force F has magnitude 20 pounds and direction angle 60 degrees, so we can decompose F into its x component and y component. These are the vectors illustrated in green in the figure on the right. So, the components of F are as follows. 20 cosine 60 degrees and 20 sine 60 degrees. dot product with the vector PQ, which has components 100, 0. That's because the wagon moves 100 feet in the positive x direction. Before we perform the dot product, let's simplify the vector f a little bit further. 20 times cosine 60 is 20 times 1/2, and 20 times sine 60 is 20 times root 3 over 2. Dotted with the vector 100, 0. We have 10 root 3, dotted with the vector 100, 0. Let's compute the dot product. That's 10 times 100 plus 10 root 3 times 0. So the work done in moving the wagon 100 feet is 100 times 10, which is 1,000 foot-pounds.